Okay, so it says live.
Yeah. Hi everyone. Thank you so much for joining us here at YouTube Live. For those who don't know about PyData yet, we are a non-profit education program of NumFOCUS, providing a forum for the international community of users and developers of data analysis tools to share ideas and learn from each other. PyData communities approach data science using many languages, including but not limited to Python, Julia, and R. So we do work in Scala and other languages as well. Well, for today, we have a great talk for you tonight called "What Lies in Sub-Word Embeddings," and I'll have my speaker give a short bio of themselves to share with you. So, without further ado, I present you to Vincent.
Yep. Okay. Hi everyone. I hope everyone can hear me perfectly correctly and stuff. So what I intend to do today is I want to explain some things about word embeddings and show you a cute little package, and I hope everyone is interested in that. But you are also more than welcome to ask a couple of questions. I believe that some of the co-hosts are looking at YouTube as well. So if there's any questions, there'll be ample time for me to answer and stuff. But first and foremost, what I'm going to do today is I'm going to talk about word embeddings. So to explain how they work, I've always found it to be just maybe slightly easier to start with something that's actually a bit simpler, which is not word embeddings, but letter embeddings. And to show you what letter embeddings can do, what I've done is I have this Colab notebook over here. And I'm not going to run the whole thing. This thing is already run. But the main thing that's kind of important is this bit. So I have a little bit of code here, and this is I would argue, relatively simple part of a neural network. The main thing that I have here is this embedding layer. And that's going to be a bit of a core concept because we're going to be talking about word embeddings. So this idea of an embedding layer is going to be rather important. What I'm doing in this notebook is I'm trying to figure out if there is a numeric representation for a letter that might make sense. And the idea is that I'm going to have some sort of algorithm that I can just give a whole bunch of text. And the idea is that the algorithm then has to take that text and afterwards has to be able to say, the letter A, if I were to represent that numerically, here's two numbers that allow me to do that. And if I have the letter B and I wanted to represent that in a very proper way numerically, well, then I've got this other set of numbers at my disposal for that. So that's what I would like this algorithm to do. The interesting thing is what the algorithm will do is it's going to start out randomly. It's just going to say, okay, all the letters and all the numbers, and they're just randomly in some point in space. What I'm then going to do is I'm going to give a whole bunch of English text to the algorithm, and it's going to train a bit, and I'll explain in a moment how the algorithm works. But we do the Keras fit predicts trick, and afterwards, after a couple of these epochs, if I were to draw the numeric representation of these letters again, a very interesting clustering phenomenon seems to occur. Without explaining the algorithm just yet, but one thing that we can at least see is that all of these vowels and consonants, they are separated out. So the P, the N, and the K, they're all sort of in one cluster. And then we've got this other cluster over here with the E, the O, the I, the U. And it also seems that automatically it's been able to detect that the letters should also be separate from the numbers. So we seem to have something of an approach here that allows us to give text to an algorithm, and then it's going to do some clustering for us. And that could be reasonably useful. So what I'm going to do is just explain how this algorithm works first, and then I'm going to explain how I might extend this idea for text in general. But I do hope as a first order thing, the fact that we get these clusters of letters, that's an interesting phenomenon. The fact that that's happening on its own. And this notebook, by the way, is readily available. So if you want to play with this is something that I will be able to share. Well, let's now talk on how this algorithm works, because I thought it was a relatively cute trick that we were able to pull off. The idea is I have a whole bunch of text, like suppose I have some text saying hello world. That can sort of be part of the corpus, so to say, that I'm dealing with. And what I then have is, over time, if you will, I have all of these separate letters. So at time step 1, I will have the letter H. You could say that the second letter that I have, that's the letter E, etc. And one thing that you can wonder is, am I able to predict what the next letter is going to be? That's a task that I might have. That's something that I could be playing with. So let's see if we can make some sort of a neural network that can do that for us. And by the way, is this big enough as far as people can read? If one of the organizers could comment on that. Just want to make sure I'm not drawing too small. Okay, no response, so I'm assuming this is okay. If it is too small, do let me know. But the idea is as follows. What I could do is I could say, well, I have this vector. And this vector is going to be all zeros. It's going to be all zeros except for maybe one index where we have the number 1 appear. And it could be that that index corresponds with the letter H. And we can then say, well, this is a sparse representation for a single letter. And the size of this array would be 26 letters plus 10 numbers and maybe like a white space token. So let's say that this is a sparse array of size 37. That's how many slots I have in this array, so to say. Well, what I could then do is I could say, well, let's hook that up with a fast forward layer. Let's just connect the two. So I could say, hey, here's something of a fast forward layer that's attached. And let's say that this feed forward layer is relatively simple. So let's say it only has about 4 nodes. But what I could do is, from a neural network perspective, I can just say, well, this on this side over here, that's my input. And then this is just some hidden layer that I'm going to be using. And potentially it's more than one. I mean, I could also draw another feed forward layer here. That's sort of the nice thing about deep learning, is you can just hook stuff together. It's perfectly fine. You can totally do that. And what I can then do at some point is I can say, well, I do want to attach at some point some sort of a label to the system. And what I could then do is I can say, well, you know what? Let's now have a final feed forward layer over here. And let's draw that one more time. We'll do that like so. And let's have this one also be of size 37. And let's also say that there's a sigmoid activation function on this one. And one thing that's then kind of cool is we can say, well, presumably, we can interpret the final layer here as predictions for the next character. And we would hope that most of these values are pretty close to 0, except maybe this one index that corresponds, in this case, with the letter E. That is something that we might like to predict. And the idea here is by taking my text and by pretending that there is this label saying I want to predict the next character, I'm able to still do sort of unsupervised learning in a way, because I'm cheating, because I'm adding a label of sorts, something that's inherent in the data. And the interesting thing, if you look at it this way, is that you could then argue that perhaps what comes out of this feed forward layer, well, that's an array of 2 numbers, because this is a small hidden layer. And you could say that the output of the 2 numbers that I have here, well, that is, in the end, a one-to-one correspondence with the letter that I've got over here. So by taking text, which is happening over time like this, and by trying to predict the next character, as a consequence, I can end up with these numeric vectors, small ones, so not huge, right? These are not huge word embeddings, they're just two-dimensional letter embeddings. But the funny thing is, if I then repeat this for a whole big corpus of text, well, what I then end up with are representations for those letters that are just nice and clustered together. And with my knowledge of language, I can confirm that indeed it has been learning a correct thing. All the numbers are just clustered together, and the consonants and the vowels, they're separate. So I could argue here that we are introducing a label, and the label is something that is in the language itself, but we do get a useful pattern emerging, and that is something that's relatively hopeful. But it does make you wonder if we can perhaps generalize this. Because if we can generalize what we have here, well, then maybe we can extend it such that we are also able to train not just for maybe letter embeddings, but maybe something like word embeddings. Potentially, if we just make this network big enough, we might also have the same phenomenon of that clustering appear, but then on meanings of words instead of the use case for a letter. So what I'm going to do is I'm just going to erase a couple of things, and we'll just explore how that might work. But I do want to just check if there's any questions at this phase, because this will be a good time to just make sure we're all on the same page. And if the co-host prefers to also be in the camera for now, that's also fine if there's a question. Just want to make sure if there's any questions now. While I'm erasing some of these things, I'll wait and check just to see if there's any questions.
Hi, so someone has asked that instead of sigmoid,
Yep.
wouldn't that be a softmax function?
Oh, yep. Sorry, you're right. I confused the two. It is softmax because that's to sum to 1. You're completely right. Yes, my bad. The main thing is that you want to make sure that what you've got on this side over here, that represents the actual prediction because it's the final layer. But yes, it's not sigmoid, it's softmax. My bad. Well spotted. Okay. Feel free to let me know if there's any other questions then. But
and there's another question. Would space be a part of vocabulary?
Could you repeat the question one more time, please?
Would space be a part of vocabulary?
It would be in this case, yes. And to be honest, you can kind of see that space is now. The downside of printing the character space is that you cannot see it. But whoops, let's just scroll down real quick. But one thing that you do see is that there's like some space over here with nothing in it. So what I'm assuming is that the space character is somewhere along over here. But the space character is indeed a character that it would predict. And because it's probably located over here, because otherwise we wouldn't have this space over here, I'm assuming that it is its own separate cluster, which would make sense. When we're going to go towards word embeddings, we're going to ignore the space. But in the case of letters, it's hard to ignore the space. But yeah, it is part of the vocabulary. But if I were to take a step back, and if I were to maybe look at this and see if I can generalize it, what I could say here, if I just erase the final layer, and let's also erase this part, but we could at some point say that I'm just going to hook this up to a task. And the whole point of that task is basically to give me something of a gradient update. The whole reason why we have these feed-forward layers be able to learn is because we have some sort of gradient signal from the errors that we're making in our predictions. Now, what we are actually predicting, that might vary. It could be the next token, it could be the next 2 tokens or something like that. But the main thing that's important is that we have something of a task over here that gives us this gradient update. And that's usually also why you invent some sort of a supervised thing that you can actually use to train this unsupervised thing. Because without this gradient update, there's no way to update these layers. So that's something to keep in mind. But I think in general, we can imagine that for a lot of the things we're trying to predict, let's assume that we're trying to predict the next token or the next few tokens or something like that. And if we then want to expand what we've got over here to not be about letters, but to be about words, well, then we can pretty much keep most things intact. The main thing that we then have to consider is that maybe this is not going to be a sparse array of size 37. This is probably going to be a sparse array that might be potentially like 100,000. Like we can have many different words. So that means that we might need to have many different indices. And let's say that I've got the word, I don't know, university. We might still have the situation that that university is pointing to an index over here. And we might have, oh, I don't know, like a feed forward layer that's 1,000 over here. Maybe we have a feed forward layer that's 300 over here, and then things will become bigger. But theoretically, at least, you could also train word embeddings this way. The main thing that we have to think about are some of the algorithmic details at this point. So one thing about this task is that maybe instead of predicting the next word, which is something that we could totally do, we can also say, hey, we want to predict the next 5 words. And another thing that you could do, which is somewhat common, is you can introduce this notion of a context. So if I have a sentence that says, I like to eat pizza, let's say that that's a sentence, and let's say that I'm interested in predicting, I don't know, the word embedding for this one, then you can say, well, in the context of the word to, I would be interested in predicting all the words that surround it. So I don't just want to predict the next token, I want to predict all the tokens that are around that one word. And you can have different labels, so to say. It's not necessarily an exact science. Different algorithms have different labels that they attach. But again, the main thing that we are doing by doing something like this is making sure that we get some sort of a gradient update. So that also means that we get to be a little bit vague about what this task necessarily is. The main thing that's important is we have some sort of label once again. So we can just play around with this idea of something of a context that we're trying to predict. And as far as gradient updates, I think we're then still good. The main thing that's kind of tricky at this phase now is, I suppose, this part, right? Like a really downside, a pretty big downside of these word embeddings this way is that we might need to have a really, really, really big sparse array for all the possible words that are in the language. And that's not necessarily something that we like. So what people sometimes do is they say, well, we might apply some stemming. That's something that you can do. You can try to say, hey, let's see if we can keep the vocabulary size down. But another thing that typically happens a lot as well is this sort of hashing trick, where the idea is as follows. When we have this token like university, let's just make sure that it lands somewhere in this array. And let's make sure that whenever I get the same word, it lands in this exact address. But in order to keep the memory small, what some people sometimes do is they say, well, let's just keep this at, I don't know, 10,000 or something like that. And yes, there is this possibility that 2 words might collide. But one thing that we can do is sort of just have this hash function appear. And then the chance of that happening can be somewhat small. But these are sort of algorithmic tricks that some people try. And what I'm mainly trying to explain with this is that you can have many different variants of this idea. You can have a slightly different way of encoding things over here, and you might have more layers over here. But it's all practically the same idea still. But these word embeddings do have a big downside. And this is where my background kind of comes in. So I work for this company called Rasa. And what we like to do is we like to really make sure that we have algorithms that are really well suited for digital assistants. So things like chatbots, those are things that we're really interested in. And we kind of have this naughty issue if you think about it, because especially in the ecosystem of chatbots, one thing that tends to happen a lot is university isn't spelled this way by a user, but university might be spelled this way with a C instead of an S. And this is something that tends to happen quite often. You can just mistype a character and that will happen. Unfortunately, even with or without the hashing trick, what you're probably going to end up with is either you're going to, by accident, point to the wrong index over here, which is a bit of a bummer. Or what is going to happen is this misspelling is causing you to realize that there's no token whatsoever that matches this. So what a lot of backends for word embeddings do is they say, well, if I don't recognize a word over here, then I'm just going to set the array to 0 everywhere, which means that your word embedding effectively becomes the giant array of zeros. And that's a plot, like I will argue that's a pretty good way of dealing with it because there's no information that is known to you at that moment. But I hope that you would agree, it does feel like a bit of a shame that we cannot, like a single character that's misspelled will cause this word embedding story to sort of go amok. And that's a bit of an issue. So people have thought about this and they've come up with different ways of dealing with this. And these are word embeddings that I find relatively exciting because the idea behind them is relatively simple. But I hope that we acknowledge that this idea of having a misspelling, that's a relatively frequent problem. It might very well also be that we see a word in the train set that we don't have in the test set. Sorry, it might be that we have a word that's in the test set as opposed to the train set. And that is also something we just want to be able to guard against. So the problem that we have is we have this out of vocabulary phenomenon happening once in a while. So what I'm going to discuss with you is how we can make some changes to this system so that we're still relatively robust against that. And I hope that you would agree. What I'm talking about here, it really matters for the English language. But I'm hoping that you would agree that this is a problem in most languages. So it's interesting so it's important that we realize how we can fix this. Before I give like a possible remedy to this, though, I just want to make sure that I have not lost anyone. So are there any questions at the moment?
Yeah, so there are two questions. The first one is what does secondary hidden layer signifies?
So it's a pretty good question. You don't technically need it. The main reason why I drew it is to just emphasize that you could have it. One way of interpreting this is you could say, well, there might be some non-linearities that you pick up this way. But if I were to erase this, the main concept would still totally work. The main thing I wanted to emphasize is that you can be flexible with the, how shall I say, network architecture that you have over here. The main thing that's important is that we have this one step where we go from sparse to dense, which is done with the matrix multiplication. That's the main thing that's important. But what possible shape we have here exactly, it doesn't matter too much as long as we have the gradient update. That's the main thing that's important. That's a really good question, by the way.
Yeah, so there's another question, which is we just predicted the next letter from just one previous letter.
Yep.
Can we expand the text by using more letters?
You could, but what I'm explaining in this particular case is that we're saying, so if you, 2 steps back. So yes, what you can do for the embedding is you can say, well, let's use the previous 2 letters to predict the next one. And again, that's sort of in line with what I've drawn. It's a slightly different architecture, but you still get that gradient signal. Now, suppose that you want to do 2 letters in sequential. I'm just going to draw it real quick. What you're going to get is you have your sparse array over here. You'll have your sparse array at time step t plus 1, and this is at time step t. And let's say you want to predict the token at time step t plus 2, right? So let's say that this is the data going in. This is what you want to predict. Well, you would typically still have this first step where you make sure that the sparse input becomes dense. And then what you have is possibly one more feed-forward layer over here where you combine the two. But the main thing you got to keep in mind if you're building your architecture this way is that these two embedding layers are indeed identical. You have to program this in such a way that if I get the letter V here, or if I get the letter V here, what comes out over here should be exactly the same. As long as you do that, you're safe. We're not doing that exactly here in this case. This case, we're just ignoring the letters for now, and we're just saying a word is a token instead of a letter. But if you want to expand your idea and still keep everything feed forward, you can use an approach that's like this. That's something you could do. So good questions on both. What I will now do then is explain how we might be able to make these word embeddings just slightly more robust against out-of-vocabulary situations. Because it's a use case. We want to be able to still be able to say something about words, even if we've never seen the word before. So one thing that we can do is we can do the count vectorizer trick. If you go to scikit-learn, there are some featurization tools available for you to extract features from text. And one of the characteristics that is in there is the ability to not just count for every single word that you see, but potentially also for the n-grams. And I'll just draw out a few. So if we are talking about n-grams, and let's say that the n is equal to 3, so we're going to do the 3 grams over here, then you might be able to realize that uni, that's a subword that we can pick. You have NIV, you have IVER, and we have a whole bunch of them. And at some point we'll come here to CIT and here to ITY. Oh wait, I think I drew one too many over here, but I hope the idea is clear. Like we can have a look at all these subwords that are in here, and potentially we do this not just for the 3 grams, but we could also maybe do this for the 4 grams, as well as for the 5 grams. That's something we can totally do. But one thing that's interesting is maybe we can represent one word not just as a single number that's listed as on or off. But what we can do instead is we can say, you know what? Let's just take all of these subtokens and let's associate those with, I suppose, addresses in this array. I'll just only draw a few of these. But that way, the definition of a token becomes the subword as opposed to the entire word. And you can imagine that maybe that gives us a more rich representation. So I'll just draw that we now have more ones in this entire system. So let me just draw that. So there's a 1 there, 2 ones over here, and another 1 over here, let's say. And the reason why this would still work from a machine learning perspective, the reason why the gradient update is still able to help us, is we can kind of have a thought of what is happening just in the middle over here in this layer. And to draw that out neatly, I am going to just need to select that marker. Because if we think about activations and that sort of thing, if I were to look at the weight that I have from this node on the left-hand side to that node on the right-hand side, because the input value that I have over here, because that is equal to 0, then I might as well not draw that arc. That arc has no weight that is going to be updating the nodes on the right. So if I were then to draw all the connections that do actually have an impact, just do that real quick. That one, yep. So these 2 weights would be activated. So would these. So would these. And so would these. And if these were the only addresses that were activated, so to say, well, then when the gradient update comes in over here, that means that these weights will be updated. And it also means that only these weights will be updated because all the other values are 0. So there's no gradient that will be able to update a weight. But because all of these weights will be updated, and because we have a single word mapping to all of these subwords over here, we do still have the phenomenon that what comes out over here is a one-to-one mapping that represents the numeric representation of this university token. And here kind of comes the cool bit. Let's now imagine that, let's say that this was actually spelled correctly when we were learning, right? So let's say universities with an S. Let's now say that I'm no longer training, but I'm in this test scenario, so I'm applying this to data I've not seen before. Well, then it's possible that I get the word university with a C, and that would mean that I still have this subword, as well as this subword, as well as this subword. I have most of them, but I am missing this one subword. And in effect, that would mean that this becomes a 0, which in effect would mean that the weights that came out of there are no longer valid. And that's a bit unfortunate. We are definitely missing some information when we do this. But notice that only a very small subset of all the n-grams of the original word are no longer in there. So that means that, yes, we lose some of the information, but because we've sort of spread our luck over all of these subwords, we actually still maintain a fair amount of the information that we learned from our original data. So that means that we have a word embedding of sorts, but one that is definitely robust against some spelling errors, and perhaps even some out-of-vocabulary situations as well. So this is actually one of the core ideas behind fasttext. If you use the Python module and you take the pre-trained embeddings, then this is what is happening under the hood. Under the hood, it's not just a single vector that we train per word. Under the hood, we actually have these subwords that are also being trained for, and that gives us some level of robustness. This would be an excellent point in time to just check if people have questions, actually.
Yeah, so I have a few questions as well.
Sure.
So is it just a skipped round word embedding, right? How about CBOW applications?
Well, so CBOW, this whole continuous bag of words, right? That says something about how we add a label here, right? We still have a bag of, well, they're not necessarily words, they're subwords on the left-hand side, but exactly how we specify the task, well, you have CBOW, there's this other one, you've got skipgram, but the idea of that is just how do we attach a label to the system? The main thing that fasttext does on top of this is this stuff. All of this, hey, let's also do that whole thing for subwords. Fasttext does do skipgram and CBOW internally, and they're roughly the same. It's just a slightly different way of declaring the cost function and the label, so to say. That's the main difference, at least from my perspective. Did that help?
Yeah, definitely. So I have another question, which is, does the prediction of next letter depend solely on the single previous letter, or does it also takes into context all previous letters as well?
So that depends a little bit on how you train CBOW and etc. Again, one thing to remember, we are no longer doing letters, we are doing subwords. And the main thing to have in mind here is this idea of context. So if I were to just zoom in on that. So let's say I want to train the word embedding for the word to. then we could say, okay, the word to is, let's do a sentence with somewhat longer letters, because longer words, because that's a nicer example. I attend classes at my university. Let's say that that's the sentence I'm interested in. And one thing that you could do is you could say, well, I want to train the embeddings that belong to the word classes. Well, and what labels am I going to pick there? Well, there's a few ways of going about it. You could say, let's just take all the words that are in this sentence, and I want to be able to predict all of these words over here. So that means that after some sort of, not sigmoid, but softmax activation function over here, I would really love it if the word classes were to go in here. Over here, I would have something that says, oh yeah, the I, that should be a relatively high probability. The word fire should be like super small because it doesn't appear in that sentence. But the word at, it will be nice if that was a somewhat higher probability. But how you exactly go about, oh, this is the context and these are my labels, you have a little bit of freedom in that. And if you look at the literature, people have tried out different approaches. There's also another approach where you take the sort of similarity of vectors. That's another way of getting a gradient signal. But given that we still have the situation of, well, one word goes in, we just have multiple words that we are trying to predict, what fasttext essentially will do is we'll take this word classes, it will take all of the n-grams, so to say, plug them in, and then still do this gradient update in the back. That's the big picture idea still. Was that sufficient?
Yeah, so we have another question. Can methods like fasttext apply transfer learning, where prior knowledge from pre-trained embeddings can be fine-tuned on a new corpus?
I would have to check the library, actually. I'm not super sure. So it definitely is transfer learning in the sense that you have these fasttext embeddings, if I'm not mistaken, for over 150 languages. So what a lot of people do as far as transfer learning goes, what you definitely can do is you can say, well, here's text, give that to the fasttext algorithm. Out comes a vector of, I think, 300 letters. And then the main thing that you do is you just take logistic regression at the end of it. Let's say you want to do sentiment or what have you. You can say, well, I don't have to retrain the embeddings themselves. I just have to add like one or two layers at the end. I think that's the more common approach to what most people do. It's what we do at Rasa as well. And the main reason why this is very common is that you can say, well, I don't have to retrain everything that fasttext has done because the training phase can be incredibly expensive. I wouldn't be surprised if there's a setting inside of fasttext that allows you to take the pre-trained ones and maybe train them a little bit further on your own corpus. It might be in there. It's just that I've never used that feature because I've not experienced the need for it. I think that's it as far as questions go for now, I suppose.
Yeah, Vincent.
Cool. All good questions, by the way. It's always nice when people ask like questions that are that make me think. So thanks for that. So I've now talked about like all the good stuff of fasttext. So this might also be a good point in time to start talking about some of the bad stuff. So fasttext definitely was like a nice little milestone because it was doing a couple of things right. But if you think about it, right? What might one of the downsides now be? Well, before we had one word, but now for that one word, if we have 3 to 5 n-grams, then we might, if it's a long word, have like 100 subtokens at some point. So definitely, if we are going to fit everything in here, maybe the sparse array just has to be a bit bigger. And if we have very big vectors, I mean, if you want to download this pre-trained fasttext embedding, be prepared. It can be between 6 and 7 gigabytes just on disk to have fasttext embeddings. So that also means, depending on what laptop you have, if you've got 8 gigs of RAM, you might be pushing it. these are not lightweight. They're kind of heavy if you think about it. So one thing that the fasttext paper does to at least mitigate this slightly is they definitely apply that hashing trick that I alluded to earlier. So there's definitely that hashing thing happening here, which technically does mean that theoretically it could happen that two subtokens collide once in a while. It's just an unfortunate thing that might happen. It will be consistent. So if two subtokens collide, then it will always collide. So there's still something that these layers might be able to learn and then sort of correct for. But definitely a very big downside of this is that these things are just heavyweight. These are not necessarily lightweight models. And then for reference, I think if you take I think they're glove vectors inside of spaCy. I don't know for sure. But if you take the medium spaCy model, I believe it's like 100 megabytes or something like that. So this is definitely like an order of magnitude larger. So that's something you have to consider. And with that in mind, you know, if I start thinking about, is this super applicable to a chatbot setting? Part of me likes to think, yeah, because, you know, we've got this out of vocabulary guarantee in there, and that's something I definitely like. But I don't like the 7 gigabyte story. Like I like my digital assistant algorithms to stay lightweight if possible. So then there's this other idea that we might do instead. And to understand what the idea is, what I'm just going to do is I'm going to write down some words, and then we're going to talk about how at least the English language works. So I'll write down astronomy. I'll write down astrology. And I'll write down astrometry. I'll write down biology, geometry, biologist, and geologist. So if we have a look at all of these words here, right, you could argue that the definition of the word can be inferred. You could split all of these words up and then understand where they come from. So astro, that has to do with, you know, the stars in the sky, etc. A bio, that has to do with like life science. And geo has to do with the study of the earth. And if the end of the word has something like ology, then it sounds like, oh, that's the study of something. If it has metry, then it's about the measuring of something. And if it ends with gist or ist, oh, then it's about the profession or the person doing the study. And the nice thing about how language works is you don't have to know every single word or every single subtoken. Very often, like words come to be by just combining two words together. So I could say, maybe if I've never seen the word geology before, well, then I can still guess what the word means. The main thing I got to do is learn what geo means and learn what logy means, maybe. And if I know those two things, that might just be enough. And with that idea in mind, maybe, right, we don't need all the n-grams. Maybe we only need a really strict subset of them. Maybe it's enough if I just know geo and logy, and that way I don't have to worry about a subtoken like EOLO. Like that's an n-gram that I don't need to learn if I have these two already. So there's also this other embedding called a Byte-Pair embedding. And what these embeddings represent is instead of doing the fast text thing where you're really trying to learn all of the subtokens, what the Byte-Pair embedding tries to do is first you feed it language, and then it will just try to figure out what are the most useful, it's using a heuristic for this, but what are the most useful subwords to just concern myself with? There's a heuristic that says, give me the top 1,000 or the top 10,000, and it will just try to find the top 10,000 subwords and only train embeddings for those. The idea being that you will have a lot less vectors to worry about, because you're only going to focus in on the subwords that are repeated across many different words in the language. And that's the idea of this Byte-Pair embedding. And it's a relatively unknown embedding, which is a little bit surprising to me, considering the fact that they're nice and lightweight. I think if you want to download the simplest version of it for the English language, it's only like 11 megabytes. So there's like definitely, and again, these are like the small embeddings, but the idea here is that you can have something that's really, really lightweight, which is definitely something that's interesting. And the way that it does it is it doesn't separate the learning phase from the tokenization phase. It's because it's really principled in how it tokenizes the subwords, it is able to have to learn a lot less. That is the assumption of the algorithm. Another thing that's really nice about these Byte-Pair embeddings is that they exist for, and I have to, don't pin me on this, but I believe there are like 275 languages that they're pre-trained on. Odds are that if you have a very uncommon language, that there is actually an embedding that's trained on the Wikipedia of that language available for download. And the package that you want to have for that is the BPEMB package. And you're able, and we're going to look at that in a moment. But that's the idea behind Byte-Pair embedding. So you still have a little bit of this effect where, hey, let's still be a little bit robust against out of vocabulary words, but let's not do all of the sub engrams, because that might just be a bit too many to learn from. Okay, quick check. I hope I have not lost anyone. Like, I don't know if there's any questions in this phase.
Yeah, so we have a question.
Yep.
How are rarely used words in English languages taken care of? Also say Unicode characters.
So English doesn't have many really weird Unicode characters. I think English, if I were to compare it to Dutch, Dutch has like, I think it's called an accent aigu, like you have the E with a little hat on top. That's definitely more of a French or German thing than an English thing. So those special characters are a little bit less of a concern. But when you're talking about rare words, you are correct in saying, well, we're not completely out of the woods, right? Because we are, by only focusing in on a subset of all the subtokens, we are limiting ourselves. So there's definitely information loss, and it's fair to say. But let's do like one thought experiment. And there's a thought experiment that we might just do in a bit, because we can live code this. But let's say I'll come up with a word that doesn't exist. So let's say zergling mitosis. Okay, zergling mitosis. It's if you're into StarCraft, you might giggle, but it's a word that doesn't exist. It's one that I sort of made up just now. However, this is probably also a really rare word because it's a word that might not exist, right? But because we have this atosis, or especially this osis at the end, you know, it kind of sounds like it could be a disease, right? And if the Byte-Pair embedding is able to learn only just this bit, what the Byte-Pair embedding will then also do for free is ignore everything else in the word. So the main thing that the Byte-Pair embedding does is if you have a word where none of the subwords are in the Byte-Pair embedding, well, then all bets are off. But hopefully we've seen enough of the English language, or whatever language we've trained this on, that we are still able to pick up the relevant parts, even if a word is rare. Now, agreed, this is a bit of an assumption and a bit of a hope, but I hope at least intuitively you do understand that we have some robustness here. A really good question, though.
Yeah, so there's another question. Taking example of a chatbot, how you are keeping context between two particular messages or two particular statement of a conversation. For example, referring he, she kind of things.
Could you, the example is he, she, that kind of things?
Like for an example, in one, let's say the first question is, what is the capital of India? And in the second question, or in the second statement, someone is asking like, what is famous there? So how you are keeping, context between statements.
It is a bit of a long story how we do that at Rasa, but I will give like a hint, at least for now. I won't be able to answer this question at length in this particular video because it's a bit of a loaded one. But here's one way to think about it. Typically, what you do at Rasa is you try to figure out, hey, what is the current intent of the user, and what are the entities that I've seen so far. So you know, at time step 1, I get some text in. And I feed that to some sort of algorithm, one that potentially uses pre-trained word embeddings. And what comes out is an intent at time step 1 and possibly some entities at time step 1. Now, the idea is that we could have something of a transformer here, or a recurrent neural network, or what have you, but some sort of system that can take the time component into account. And we could say, well, you know, the output of the algorithm that does the intent detection and the entity detection, that's just input for this transformer. And then it's just going to predict the right action to take right now. And then the user gives us another bit of text. That's going to, again, go through some sort of algorithm. And it might still say, well, this is my intent at the second time step. And it might be the case that there are no entities at the second time step. But this transformer still has access to that information because that was passed in earlier. You can have a recurrent system that is able to take this into account, also to add context, so to say. Our preferred method at the moment is to use a transformer for that. We have this thing called a TED policy mechanism inside of Rasa that works this way. The main driving component there, there's a little bit of star space in there, but the main thing, I would argue, is this transformer. So that's a way to deal with some of that. How do I keep context in mind from previous time steps? This is one of the main tricks that we use. I have written a blog post or two about this, so feel free to reach out to me on Twitter if you're interested in that.
Yeah, so another question related to the previous one.
Yep.
So how you're handling these statements with which do not have sufficient amount of information, like statements which have a sense of vagueness in them?
Yeah, that's a good one. So these Byte-Pair embeddings, of course, are not perfect, right? But I think I might have a nice example. Suppose we're doing sentiment analysis, and someone, like this is a really British stereotype statement, but let's say that someone says, I suppose that there are potential downsides. I don't know. And let's say that we're doing something of like sentiment analysis or something. Then I would argue if that sentence is in like a report that describes how well a company is doing, then I would say, okay, that's negative sentiment. That said, none of these words separately indicate a really strong negative sentiment. And odds are that perhaps the word embeddings that we have at our disposal for those words also do not fully capture a negative statement. It's the combination of these words together that might make us believe this instead. So one way of dealing with this is very similar to what I've shown you earlier in the previous question, because let's say I'm going to have to erase some of this stuff, actually, because there's not enough space. But let's say, erase. So let's say I have a sentence, and I've got my word vector for the first word, for the second word. So let's say that's the first one, that's the second one, that's the third one, right? I have that all the way up until some number n. I mean, also here you can feed this into something that is potentially recurrent, or, and again, that's more my preference, a transformer block. Well, you can just pass that in as input, and then it might be able to say, okay, this order and this combination of words that I'm seeing, that is something that might be slightly suspicious. And this is also one of the mechanisms inside of BERT. The idea is that you look at a word in context of the words that currently surround it before that you fully say, oh, this is the word embedding that belongs. So the idea is you get these contextualized word embeddings out if you do that. And then it might be the case that here you actually are able to translate the subtlety into something that's more useful and something that indeed can be picked up by a sentiment classifier later. A bit outside of the scope of what I want to continue on. But again, a good question. This is how I think a lot of people go about handling things like subtlety. I want to argue in the realm of digital assistants, subtlety is less of an issue, mainly because users tend to quite literally give a command to a chatbot to go ahead and do. It's rather not it's not really typical to see a user give really vague commands to the chatbot, because it's not in the interest of the user to do so.
Very well. So next question is, can we use Byte-Pair and fasttext together?
I mean, there's nothing stopping you. I mean, of course, I cannot really come up with a good use case for it. They should learn similar things, right? So that's one thing. But definitely one thing that you can do is you have some text, and then you say, oh, I want to get a big word embedding out, so I'm giving it to fasttext, I'm giving it to Byte-Pair. And these both give you vectors. Let's say the Byte-Pair gives you a vector of size 100, and we get a size 300 here. And one thing that you can do is you can just concatenate them together, and then you've got a large array of size 400, the first 300 of which are fasttext, and the other ones are just the Byte-Pair ones. I mean, that's something you could do. Something tells me it's not what you want to do, because typically you want to keep things lightweight if possible. I mean, we could go ahead and also just add spaCy here and BERT, and we can party on and just keep stacking stuff together. But stuff is going to get quite heavy, which usually is a reason why people don't do this in production, I think. I've not tried, I should be honest, but it's a reason why I can imagine people don't do this in production.
So I have one more question, which seems pretty interesting to me. How can we compare these embedding approaches to see which one makes more sense for our application, or when change training process?
So that's the hard part. and it's also exactly what I wanted to talk about in this next bit. One thing I just want to check, time-wise, how much time do we still have?
Yeah, we can take another 50 or 40 minutes, 50 minutes.
Okay, now we should also have a break, but what I'll just do is I'll briefly touch upon this point. We'll then have a 5-minute break or so, and then I will show you a tool that might help answer the question, because the question is really good. Like, what is actually in these word embeddings, and when are they useful for stuff that we are actually interested in? And I'm going to have to take a small step back and talk a little bit less about the algorithms and a little bit more about qualitatively what patterns are that it could be learning. But I am going to come back to your point. So if I just take a sentence, something like, I pet my dog, for example, right? That's a sentence you could have in English. And you can also have a question, another ones, like she pets her cat. Right? So these are two sentences. And one of the things that we can imagine these word embeddings to learn is the fact that this word pet for petting, so to say, that verb, that might get associated with this word dog, just like how the same verb here gets associated with cat. So dog and cat are probably used in similar ways in sentences, and that is why probably if we're going to do this clustering thing, they're going to be together. They're going to be close to each other. And we can maybe say then that if 2 points are close to each other in embedding space, that they are indeed very similar. And that means that we have summarized the language in some way, and that is where the pre-training kind of comes from. However, we have to be really careful here. And the reason is that we might be picking up some patterns that we aren't necessarily interested in. So what I hope you can imagine is that cat and dog, right? That should sort of be in a cluster, so to say. And probably what should also be in the cluster there is just the word animal. Because if a lot of sentences will say, oh, a dog is an animal and a cat is an animal. So a lot of these is a relationship, like a dog is an animal, a cat is an animal. We should expect clusters of those words to at some point appear. And similarly, I hope you're also able to imagine that we have hospital. and doctor and nurse. And that's because doctors and nurses are part of a hospital. Just like we have an airplane, and that usually has a turbine in it. And the reason why they are similar is because a turbine is part of an airplane. However, one thing that we should be aware of is the relationship that we have here. A cat is an animal and a dog is an animal. Doesn't hold for everything that's in proximity to each other. And that is because a turbine is not an airplane. Sure, I expect those two words to be close to each other in embedded space, but the reason why they are close is because they have a different relationship. And that's what makes these clusters a little bit tricky, because the distance that we get doesn't necessarily have the same reason. And it gets worse. So another thing that I expect to have inside of these word embeddings, and that is to say, not everything that glitters is gold. We have this word good, and we have this other word bad. And in this particular case, you can say, they should be similar because they're both judgments about something. But if I were to think about the meaning between those two words, then it couldn't be more different. They're like the exact opposite of each other. However, because they are both ways of describing something, in embedded space, you will get them together, even though the meaning is opposite. And the same thing you'll have with love and hate, and hot and cold. If hot and cold are both ways to describe a beverage, and people are describing beverages, then the algorithm is probably going to think that hot and cold are maybe very similar. And this is where it becomes really tricky if you're going to use this as a pre-trained step. I mean, yes, there is some knowledge that's learned, but the algorithm might have to compensate for some of the stuff that's in here, because the pattern that you're trying to predict yourself might not be the thing that we're training on. And that's usually where some of the tricky bits happen. Another reason why you get this is if I take a word like Python. I mean, Python has multiple meanings. It can be a snake. It can be a programming language. But it can also be a very popular television show from the 60s and 70s. And the downside is that the algorithm has to figure out one particular point for the word Python, even though it can have substantially different meanings. And also that is something that we should expect in these word embeddings. Another one that I think is very interesting as well is you've got Brussels and the EU. Let me just write that down. So you have, like, if you're reading a newspaper, when people talk about Brussels, they're sometimes talking about the EU. However, the word Brussels literally doesn't mean the EU. That would be a false statement. However, if you read a newspaper on decisions being made in Brussels, because it's also the headquarters of the European Union, you might get an algorithm that's confusing Brussels with the European Union, even though European Union can mean different things. I think there's like from all the examples that I know, I think there's like two examples that are definitely worth to mention, because there's a couple of horrible examples of this in language, but I think the word sanction is particularly nice. So the thing is, you can be sanctioned to do something, which means that you've gotten permission to do something, but you can also sanction someone else, which means that you're removing permission from someone else. So that means that we've got one word that has two meanings, and both of which are the opposite of each other. I mean, you are going to have to admit that then maybe whatever the embedding is for that word, like, we shouldn't associate too much meaning with it, right? That can be a dangerous thing. It's not ground truth, so to say. And there's another one. So we have book and read. We can imagine that a book is very similar to reading, because when you're reading something, and very often you're reading a book. However, you can also book a hotel. But the issue here can be that in language, probably the word book usually refers to the noun that is in this situation, and less often to this situation. And where that gets really tricky is that book can be both a noun as well as a verb. And when book is a noun, those are situations where it's most associated with another verb. So also here you get many of these tricky situations. And I have a colleague, if you're interested in this sort of thing, by the way, I have a colleague called Thomas. He works at Rasa, and these are examples I took from one of his slides. But these are things that Thomas and I sort of talk about. I'm half in the research team, and when we talk about word embeddings and can we actually use them, it's not all green hills and rainbows. Like, these are things that we are worried about because you might get word embeddings that have been learning the wrong thing. And another thing that we should keep in mind is that a lot of these word embeddings are trained on something like Wikipedia. And especially if you're making a chatbot where, people are talking on the internet, there might be a lot of slang. Maybe being pre-trained on Wikipedia is a bad thing. It's kind of weird to say, well, we have a body of text that's really different than what we're going to apply it to. But because there's so much data there, we'll just take the pre-trained word embeddings from that. That statement is not without risk, right? There's still something that might go wrong there as well. And finally, and that's actually a big red flag, one of the things that unfortunately these word embeddings do exhibit is bias. So you've got some of these examples like a man is to a doctor. And then if you're a woman, then you're probably closer to the term nurse. And presumably that might be because historically there are more bodies of text where women are nurses and doctors are men. But that's a wrong assumption in general. There's plenty of women who are doctors and there's plenty of men who are nurses. And one of the things that this phenomenon might allude to is that these word embeddings do tend to maybe amplify some of the bias that we have in language. And even if we train on something like Wikipedia, Wikipedia is not without bias. I think even if you take Encyclopedia Britannica, there's bound to be bias in there as well. So especially if you're going to be using some of these tools to, do things like resume parsing, be aware this is a huge issue. I wouldn't just blindly use these word embeddings without just making sure that maybe it depends on where you apply these word embeddings to some extent. I can imagine that there are areas where you can do a lot more harm with word embeddings than other areas. But I wouldn't be naive about them. Like, I do want to emphasize that there are some dangerous things that are in here. And we shouldn't assume because some third party spent $1 gazillion on getting these pre-trained embeddings that they are therefore perfect. Yes, they summarize a whole lot, and that can be very useful. But we still have to be mindful in the application here. And this is also where I figured I should start making an open source package, because I really like the idea behind word embeddings. I think that in the end, there is something cool that they do. They do tend to summarize language to some extent, and I think that has merit to it. But I really do want to be able to quickly check what actually is in these word embeddings. Because hopefully with these examples, you do recognize that, yeah, we might have some things that we should be concerned about as well. And I would really like to be able to pinpoint and visualize some of these things easily. And what I would also like to be able to do is just maybe compare the spaCy embeddings with the fasttext ones, with the Byte-Pair ones. Like, I have multiple options for word embedding, so I'd like to be able to compare them as well. So what I've done is I've created this package called whatlies. And the idea behind the package is to literally figure out what lies in word embeddings. And what I would like to do after a short break, if there's no more questions, is just give you a brief demo of what whatlies can do. And hopefully it will also make it easier for you to play around with word embeddings yourself. Whatlies also has a little integration with scikit-learn, so you can quite easily run some of your experiments as well. But the main goal is that we have some visualization tools to help us understand these word embeddings just a bit better. Before doing that, let's just check if there's any questions. And after that, we'll have like a 5-minute break before I do this coding thing.
Yeah, so I have one more question, which is earlier you mentioned using Wikipedia as a corpus. However, the uses and meaning of some word change over time or become time point from where to pick the reference word ensured.
So I only got part of that, unfortunately, but would I be correct in saying you're interested in knowing, hey, what should we do because language is a moving target? Is that sort of like it might get old? Is that the gist of it?
Yeah, so the question is, however, the usage and meaning of some word change over time
Mm-hmm.
or become archaic. How is the time point from where to pick the reference word ensured?
I think that's an open question, to be honest. From the top of my head, the main thing that I can think of is, well, just retrain once in a while. Um, I think language doesn't change. I mean, it changes to some extent, but I do think that a lot of words don't change too much because otherwise language wouldn't make sense. The main thing that you want to be aware of are things like new words and such. But the main thing that you could do that I'm aware of is just retrain more often. But it's an open question, I think.
Yeah, so we can have a break for now.
Okay. So what I'm going to do is I'm going to go downstairs to get a cup of water. But let's all be back in like 3 to 5 minutes, something like that.
Uh, yeah,
Sure. So I'll be back and I have water. If people have questions, I'll also be here to answer some. But we'll be back in a bit and then a little live code demo then. Cool.
yeah, Vincent. So guys, he'll be back in 2 to 3 minutes. Meanwhile, if you have any questions, feel free to post them in comment box or any findings or anything that in particular you want to ask, feel free to post them in comment box. In 2 to 3 minutes. Meanwhile, if you have any questions, feel free to post them in comment box or any findings or anything that in particular you want to ask, feel free to post them in comment box.
There we are. Okay. So I am back. If people have questions, now might be an okay time. We still have a couple minutes.
Yeah, hi, Vincent. So I have a question,
Yep.
which is related to the model size of fasttext model.
Yep.
So recently for a project in my firm, we are using fasttext to build model, and I came out with the thing that the size of the model is like pretty large, ranging from 100 MBs to a GB. So then we came up to a thing called quantization of model, and in that we noticed that while we do quantization of the model, then the performance got dropped by a few numbers.
Mm-hmm.
Sometimes numbers are sort of significant, and sometimes they are like we can ignore them. So any thing that you would like to advise, or kind of suggestion that you would like to give on that?
Yeah, so I think the idea behind quantization certainly has merit to it, right? Like we like having stuff lightweight. Then that stuff's fine. I like that kind of research. One thing I do wonder though. So would I be correct in saying that you've got a situation where you've got your fast text as input, that's what's being passed into the neural network model. So we have a couple of layers here, so to say. And then out here comes a prediction, and then we have sort of this feed forward. Is this similar to how your model works in a rough sketch, or is it substantially different?
Yeah, we can take this scenario.
Okay. Well, then, if we have fast text on this side, and then you've got your feed forward layers over here, depending on the library that you are using, if you're going to apply quantization, it's mainly going to be applied to this part. I mean, the layers that you actually have control over. That doesn't necessarily mean that this part becomes more lightweight. That depends on how you've implemented that. And it also potentially means that if you're applying quantization, this can lead to a limited effect as far as model compression goes. That's something that, because it's only being applied to part of your system, so to say. One thing that you can, of course, play with is if you are going to quantize more. So that means that your weights are going to become more and more sparse is not the right word, but you quantize your weights more and more. You could maybe check, hey, could we have them maybe more wider layers? It's something you can maybe explore. That might, if you're quantizing properly, you might still allow for more patterns there. But this is about the most intelligent thing I can say about it, because a lot of this stuff is try it out on your own data set, and if it works, it works, and otherwise it doesn't.
Yeah, so I have one more question, which is kind of seems interesting to me. So the question is, does Rasa use BERT, GPT-3, or any of the newer models?
Not really. I think GPT-3 is, I think, the OpenAI thing, right? If I'm not mistaken. So I think it's I think I read the article, and GPT-3 I think is from OpenAI. I could be wrong, but I believe that they're building a service now for those models. Like we have support for BERT, and we definitely allow you to write your own components. So if you're interested to have the most fancy model out there, you definitely can. But we've noticed two things. One is our users really like it if they can run this stuff on commodity hardware. If you have to buy a couple of GPUs in order to run a model, that's already a reason for a lot of users to not consider it. And another thing that we've noticed is some of the algorithms that we've made, the diet architecture in particular, that seems to work quite well, even if the input is just count vectors. Especially because we're in the situation where we have to support pretty much every language on the planet. Then it's nice if you have systems that if you just have count vectors that they still work. And we actually have users where, as a starting point, that's actually enough. So I like to think that, especially stuff that I focus on at Rasa, is to keep things a little bit more on the lightweight side of the spectrum. But also, we don't do anything properly generative in the sense of just give a text and it just returns some text back. We have this notion of an action that is relatively constrained. So only a certain set of actions can be taken by a chatbot, and it's both an accuracy mechanism as well as a safety mechanism. If you look at some of the GTP3 stuff, we don't want to have an algorithm that accidentally starts cursing or accidentally says heavily biased things. And like a lot of these generative algorithms have shown that they're capable of that kind of behavior. So that's why we're a little bit careful in that area.
Yeah. So one more question, which is related to which I want to ask. So, do you want to suggest anything that that will be sort of helpful for model interpretability, or in case of fasttext model?
It's a pretty good question. I think the moment that you use word embeddings, you do have to admit that some of the interpretability is thrown out of the window. Because they're vectors of 300 long. You don't necessarily know exactly how these clusters appear. That really depends on both the algorithm as well as the data set they were trained on. So I wouldn't want to fool myself too much thinking that I fully understand these word embeddings, even though I actually study them. I guess if you want to go for interpretability, count vectors and then a simple model probably is the thing that you want to go for. The main thing, I suppose, for interpretability that I think you should focus on are more things in the realm of do we understand the scenarios when the algorithm fails? For example, one thing, if we just have a look at what we have over here, like a typical scenario where some of this language stuff can fail is if you are training these layers that we've got over here on text that's in your train data. So let's say, suppose you have a chatbot. There's a couple of these conversations that you've had in the past, and that's what you're training on. And then a user, and let's say that we're building a chatbot for a financial system, and usually we handle frequently asked questions. But then at some point, there's this one user that says, I got scammed. With a spelling error, let's say. Let's say we have a user that says, I got scammed, and we're giving that to a frequently asked questions chatbot. I mean, this will be a pretty bad time for the chatbot to reply something back saying, hey, how are you doing? Like that would not be an appropriate action. However, if we never saw a statement like this in our training data, you want to maybe not concern yourself too much about accuracy and maybe start thinking about these things like fallback scenarios. Like when at some point do we say, well, the input that we get here is simply something that we've never seen before in our lives, so we shouldn't blindly make a prediction. There's something of an outlier detection thing you can sometimes add to your NLP pipeline that can help out in production. It's this phenomenon of, hey, this is something we've never seen before that you typically want to catch. And understanding when that happens is usually very useful. Okay. No other questions?
Yeah, so we can move ahead for now.
Cool. How much time do I currently have? Because it feels like we're nearing the hour and a half, right?
Yeah, almost.
Okay, so I'll give you like a quick demo of whatlies then. If people still have questions, I'll be around, but we should be wrapping this stuff up a little bit. So what I've got here is a Jupyter notebook. And let's make it a little bit cleaner. What I've got here is the whatlies package, and what whatlies allows you to do is it allows you to say, hey, I have a backend that can generate word embeddings. Currently, we implement Byte-Pair, fasttext, spaCy, gensim, and via spaCy, we also allow for some of the BERT stuff. But the main thing that's kind of cool that I can do is I can say, hey, I've got this Byte-Pair language, well, let's say fasttext, and I can give it a word like Pokemon, and I get an embedding back, and the embedding has a name as well as a vector. And this is a convenient data frame, if you will, to start playing with these word embeddings. Another thing that the language allows me to do, which I think is relatively cute, is I can do things like, I want you to retrieve the most similar words. And then I can say, hey, I want to have universities, where I misspell university with a C. And what you can then see is that fasttext, for example, it's still able to capture that it's about university and that sort of thing. But you also notice that because we've got this token cities in here, that it's also able to say, it's about places, maybe. That's something that it's picking up. And what you can then also do is you can ask the exact same question to perhaps spaCy, And then you'll notice that spaCy, it's having a bit of trouble because this vector that we have over here for universities, that's a token it's never really seen before. So if I were to just check the vector for that, you'll notice it's just all zeros. So the idea here is that we just have this library where relatively conveniently we can say, well, we've got these embedding backends, so to say, and we can just do some visual stuff with them. In particular, we are now using the English language, but some of the Indian languages are also definitely implemented in some of these backends. One thing I suppose that's actually kind of cute to show you is I could do something like zergling mitosis. I can do that for fasttext. And I can also do that for the Byte-Pair language, just to get the impression of the difference between the two. And one of the things that we see is that because there's a capital letter in here, fasttext thinks that it's about a person, and it's totally overfitting on this part of the word that doesn't really exist. But we also see that the Byte-Pair language actually just tends to focus in a little bit more on this OSIS part, and is therefore able to recognize that it's a little bit more about diseases and symptoms and diagnoses and that sort of thing. So this already helps you understand a little bit what these word embeddings might offer, and I think that's already quite useful and valid. But some of the other stuff that I would argue is also kind of like a cute little trick. Let's show that. Is you can also play around with these embeddings. So one thing that you can do is you can say, hey, from the fasttext language, I would like to get the embedding for king. And what I would like to have happen is I want to subtract from that the embedding for man. And let's then add the embedding for woman to that. That's something that I can do. And this is, again, an embedding object. And again, like I think the norm is also, the vector is something I can also just have a look at. So that's something that I can analyze. What I can also do is I can then say, well, this new vector, could you just get me the most similar words to whatever we end up with here? Then we notice that if you're interested in what the most similar word here is, depending on what papers you might have read, you might have been taught that the most similar word here should be queen. And queen is close, but it's not the closest. We're still closer to king than we are to queen, even if we do this minus man plus woman calculus, so to say. Anyway, so this is a feature that I think is relatively helpful. Another thing that you can do is you can also just say, hey, here's a list of words. Please give that to the language backend, and then what I would like to have is just some convenient plots. So that's definitely something that we do. We have these correlation plots that you could go ahead and draw. And another thing that I think is also relatively cute is when you have these vectors. So let's say in a very high dimensional plane, we've got this vector for man, and we've got this other vector for woman. And this other vector for, let's say, king. What I can go ahead and do is I can project the word woman onto king, and I can project the man, the token for man onto the vector of king. And what I then potentially have is this x-axis to plot word vectors on. And then you might, and this is a hypothesis, but you might be able to capture some of the meaning this way as well. So what we then offer are these interactive visualizations where you're able to properly zoom in and out, and you can just have a bit of a look on how these word embeddings are related. That's something that you can go ahead and explore. But what you can also do is apply some transformations like principal component analysis beforehand. And one thing that you can then very clearly see is that in this particular case, words like prince and queen, they're very close to each other. And then we also have this little cluster here of like cousins and brothers and that sort of thing. But then we get a whole bunch of non-related words down below. But you can kind of get an impression of which clusters perhaps appear inside of these word embeddings, which is also kind of nice. So there are many different features. You can also compare word embeddings with each other. So you can say, hey, I've in one word embedding, brother was over here, and now it's over here. And these are all things that you could go ahead and play with. The main goal that I have for this package for now is that we just make it easy for you to explore word embeddings. In the next phase, what I'll be doing is I'll be building tools to visualize and quantify how much bias there is in word embeddings, especially things like gender bias, race bias. These are things I would like to be able to quantify so that I can maybe judge whether or not for the use case that I'm interested in, if the word embedding is appropriate. So these are things that I'm interested in adding to this library. And if you're interested in exploring some of these embeddings for the first time, you might enjoy playing around this library because it also helps you explain how these word embeddings work to some stakeholders. This was the and this was the 10-minute demo to whatlies, I think.
Vincent, I have a question.
Yep.
Would I able to input word embeddings or embeddings that I trained in a custom model into whatlies?
It depends on the backend. So spaCy actually has some support for some of the BERT models. And if you have, for example, trained your own BERT model that is spaCy compatible, then you can just load it in. So that's a feature that I already have. I still have some like extra backends I want to plug into this. So the Hugging Face is definitely like one that's on the roadmap. The universal sentence encoder from TensorFlow is also one that I've got on the roadmap. So there is some light support for BERT already, but you can expect more in the future. One of the things that I also allow in this package, by the way, if you want to have a sentence like I code in Python, or you have a sentence like Python is snake. What my library then also allows you to do is say, well, in the context of this sentence, I want to get the embedding for Python. And in the context of this sentence, I would like to get the embedding for Python. So you're able to say, well, I have a sentence of text, but I want to have that particular word. That is also something that I do allow.
And apart from this, what all other features that you are planning to incorporate into the library?
So one of the things that you can already do is you can, if I'm not mistaken, you can already. Well, let's go to the documentation page for this. What lies Rasa, and then you should see the documentation page, and there we go. So one of the things I want to add just to the documentation page itself is just a bit more of these observations. So just lessons that you can learn from, hey, if you have this use case, which word embedding should you use? So I want to research that a little bit and just want to make sure that that's properly documented. We definitely have the bias thing in here. We also have some of these interactive visualizations that are kind of nice. So there's also some visualizations that I'm currently working on. One of the nice visualizations that I've got over here, one of the nicer things, if you want to have three-dimensional data, we kind of have these sort of interactive matrix plots that you can go ahead and play with. So if you have somewhat more high-dimensional data, that's something that I can do here. There's also some support for transformations. So if you want to use UMAP instead of principal component analysis, or TSNE, like I have support for some of these transformations as well. But the main focus, I suppose, for the future is the bias. Like that's the main thing that I'm also concerned about. So that's the main thing I want to play with. I suppose one feature that's also relevant to mention is, and you can check that out in documentation, like it's not compatible with the scikit-learn grid search, unfortunately, and that's for many reasons. But one thing that we do make relatively easy is if you just want to use the spaCy language or fasttext or what have you, just for like a quick hack, you can just use that in a scikit-learn pipeline right now for whatever language that we have available. So Byte-Pair has like 275 languages that are at your disposal. But you can just go ahead and try to use spaCy or whatever language backend to make your scikit-learn pipelines just aware of these word embeddings as well, which can be a really easy, quick way to get started too. I don't know if there's any other questions.
Yeah. I was speaking on mute.
Oh, sorry.
So I have another question, which is, can we measure and rely on similarities between words on just one dimension of their word embedding vectors to capture the relation?
Well, so if you take the distance between two word embeddings, then you do measure distance. The question is, what does the distance mean? So, for example, love and hate will be really close to each other in embedding space because they're used in similar ways in texts, typically. But the meaning of the two words couldn't be further apart. So you can measure distance between words, and you can say something about similarity that way. But unfortunately, it depends on the words what that similarity might mean. And that's an unfortunate fact of some of these word embeddings.
Okay. One more question. So do you have any plan to incorporate the Unicode embeddings into?
Unicode embeddings. Let's have a look. I'll have to Google them just to make sure that if I understand what we are talking about. So these are character embeddings. Would I be correct in saying that?
Yeah, sort of.
So the thing is, I tend to add backends whenever I think that they are useful or interesting to explore. So the Byte-Pair embeddings were implemented in like a couple of hours because when I heard about them, they sounded like an amazing feature to add. And like my role is also a little bit in between the developer relations as well as the research team. So I do a little bit of work in both. One thing I do think is fair to mention is my interest is in the digital assistant chatbot realm. So I'm a little bit more interested in things that are lightweight. I prefer those to things that are inherently very heavy. But typically what I use this package for as well is I have this other package called Rasa NLU examples. And I think that's going to be relevant if there's any Rasa users listening. This is a package I started last week. It's something that's live now. But typically what I do is I first add an embedding to whatlies so I can kind of explore it. And if I like the features that I see, then I make sure it's available as a component inside of Rasa. Well, not inside of Rasa, but as part of this Rasa custom components package. So you use fasttext or the Byte-Pair embeddings. You can already do so in Rasa. But I like having them in both packages because if I'm going to be making them available to the community, I would also like the community to be able to check out what's in these language embeddings to see that they're appropriate for their use case. But the Byte-Pair embeddings, they are available in 277 languages. And if you go to their website, you have to, I think, scroll down quite a bit, unfortunately. But there's a lot of languages. And I wouldn't be surprised if there's a couple of dialects of Indian here as well. So there's definitely something to play with.
Yeah, so one last question. So anything that you would like to share, like how you're training the model, like things that are using a neural network or kind of dropouts or which all things that you're using?
You mean me personally or Rasa?
For this particular library, whatlies?
So I don't do any training actually. They're all pre-trained. I only actually so the Gensim, you can use libraries like Gensim, for example, and I do support the Gensim count vectors. But typically, the training happens either by a third party or like I do allow you to supply your own language embeddings, but I don't do that personally myself. I'm a little bit more interested in other people who've trained on, say, Wikipedia, and then looking what the embeddings behave like. The main advice I have is just to keep it as simple as possible for as long as possible. It's a really big rabbit hole you can fall into if you just, oh, let's try BERT, let's try the new fancy model. All that stuff is great. But the main thing in practice that you got to be worried about is how your users interact with the software that you make. And it's very well possible that the data set that you collect in the beginning does not represent how users eventually are going to interact with either your chatbot or your sentiment analysis tool or whatever. So I would focus on that first and foremost. Like, get the pipeline running, but then immediately try to just look at the conversations you have with your users and just try to learn from those. Because even a grid search can overfit on the data set if you're not careful.
Okay, let's wait for 1 more minute if there are any questions, and then we can wrap up.
Yeah, sure thing. So I guess one thing to mention, like, my name is Vincent. You can find me on Twitter. So if you type Vincent Rasa, you should be able to find my Twitter handle. Any questions that you might have on some of the stuff that I've shown you, just send me a message either on LinkedIn or on Twitter. I'll gladly answer. And if there's any features that you're interested in or things that you think are missing, just reach out to me, and I'd love to hear what you think.
Yeah, so I think this is it. We do not have any more questions. So yeah, so if people will have questions, then I'll ask them to have a conversation with you over Twitter. So let's wrap
Perfect.
it up. And yeah, so Vincent, we are grateful to you for sharing your time with us. In this time, we had really good questions and answers coming. Thanks a lot to those who joined us live. This talk shall remain on YouTube. And thank you once again, and hopefully we will connect again soon.
Sure. No, thanks for having me, and yeah, have a good one.
Yeah, thank you, Vincent.
Ciao, ciao.